Hello, so today we're going to be looking at solving the check permutation interview problem, I guess. This can be found in page 90 of the book Cracking the Code Interview, and it's to do with permutations of strings. So this is the problem right here. So we have given two strings, write a method to decide if one is a permutation of the other. So to start off with, a permutation is basically just a rearrangement of the characters. That's basically it. So the word act and the word cat, it's the same characters that have just been rearranged. So to just make it clear, we're just going to define what a permutation is first. So a permutation of, let's say we have two strings, string S and string T. So what this means is that strings S and T, just rewrite that, string S and string T have the same frequency. Oops. I'm going to try and be a bit more clear when I write. Frequency of unique characters. And frequency just means the number of times the character appears in the string. So, for example, like I said before, the word cat and the word act, they each have one A, one C, and one T. So they're considered permutations of each other. Another example is actually, if you know what anagrams are basically common permutations. So, for example, another one would be the words state and taste. So, state and taste, you can see that they have one S, two T's, one A, and one E each. So they're considered permutations. An example of words that wouldn't be considered permutations. So, example, the word woman, the word man. Woman has all the characters that man has, which is one M, one A, and one N. But woman also has two additional characters, W and O. There's one W, one O, while man has zero Ws and zero Os. So these would not be considered permutations. So another thing that we can actually identify from looking at these examples is the fact that words that are permutations have the same number of total characters or the same length because they have the same number of each character. So another thing that we can say is string S and string T have the same total number of characters, or that they have the same length. So now that we've identified the problem, we're going to be trying to solve it kind of using this process. So we've had a look at some examples and we've looked at the problem. So in terms of brute force, the most obvious brute force way that I can think of doing this is, and I'm not going to code this one because I just know immediately that it's really bad, is to generate and store all permutations of string S in an array. And then the next thing to do is to try and find string T match in the array. So what I mean by this is if we had the word cat here, I would store every permutation of cat in the array. So we'd have cat, we'd have CTA, we'd have tac, we'd have TCA, we'd have act, and we'd have ATC, traffic control, I guess. So we would store all of this in the array, and then if this was string S, for example, so these are all the permutations. We had string T, which is act. We would try and search this array for act. We would find it here, and we know that string T is a permutation of string S. If we had another word like ABC, we would search the array, realize that it's not there and it's not a permutation. The reason I wouldn't do this one is because it's got a very high runtime. Firstly, I'm not 100% sure on this, but I think even to generate all permutations, it takes something like n times n factorial steps if n is the length of the string. And then another issue is the fact that we would have to find, we'd have to search for a string in the array. And the complexity for that is the number of items in the array. And if you want to just look at the number of permutations a string has, it's n factorial. So for example, here it's a string of length 3, so it's going to be 3 times 2 times 1. And as you can see, we have 6 permutations right here. So we'd have to do we'd have to search through a maximum of n factorial items in the array. And then to check if two strings match, we have to go through each of the characters in the string. So we'd have to go through n characters and try and see if they match. So this is a very, very big runtime. So this is the brute force solution, but we're immediately going to try and do something better than that. So let's look at some optimizations that we could do. We don't, I'm not sure exactly what a bottleneck is, but I don't think we have any here. Or I guess the bottleneck would be going through each of the permutations because it's factorial. Unnecessary work that we're doing, definitely. To check if two strings are permutations of each other, they only have to follow these two rules. It's not actually necessary to generate every permutation and check for it. So that's something that we can avoid doing. Duplicated work, we don't really have any of that. We don't have any unused info. We've read the whole thing carefully. So the next thing that we can do is try and solve it manually on an example. That's what I'm going to do next. So let's just, so this is, I'm just going to be solving this as a person. So let's go with something that we know is an anagram. So let's go with listen and silent. So string s equals listen, and the string t is silent. So the first step I would do is, because we have this rule right here, we can immediately use that to try and eliminate, to try and avoid any further work. So string s and string t have the same total number of characters. So if I look here, this has 6 characters, and this one also has 6 characters. So we can see that that check passes. And what I would personally do for this is, especially if I didn't want to use up any more space, my suggestion would be to sort S first, then sort T, and then just compare each of the characters. So so S sorted, it would look something like this. So we'd be sorting them alphabetical order. So we have E first, then I, then L, then N, and then S, and then T. Then if we do T sort, so if we sort T, I'm just going to compare sorted strings as the third step. So if we were to sort T again, the first character would be E, next character would be I, next character would be L, N, S, T. And the final thing we just compare these. So these match, these match, these match, these match, these match, these match. So we know that S and T are permutations. And as we can see, even in this manual example, we can see that we never had to generate all the permutations. So we can build an optimized solution based on this. So yeah, let's try and do that. And we're going to be doing a time versus space trade-off because we're going to need to use up some space at least computationally to be sorting these strings. So this is going to be the more optimized solution. and it's going to involve sorting. So the method is going to be, the return type will be a Boolean because it's going to return true if string s and t are permutations and false if it's not. I'm just going to call it check permutation based on the name of the problem. It's going to take string s, string t, and the first thing we can do immediately is to check that they have the same length. Because if they don't have the same length, we immediately know that they're not going to be a permutation, so we can avoid doing any future work. So what we can say is here, if s dot length is not equal to t dot length, then return false. So that's the first step. The next step would be to sort s and then sort t. So the way that we can do this is I would probably ask in the actual interview if I'm allowed to modify the string directly. If I'm not allowed to do that, I would duplicate them, I guess, which would use up more storage, I guess 2n storage if these are the same lengths. So I'm going to say s.sort followed by t.sort. So we're going to sort both strings. And we'll use something like quicksort, I guess, for this, which is the most efficient way. And then what we can do is basically just check through the characters. So we can just have a for loop, and then we can have start off with index 0, and then we can go until we can go through every character basically. So we go from 0 to the length, and we increase I by 1 on each iteration. And what we want to do here is say if s I, so the character in string s at index I, so index I was 0, for example, we'd be looking at this one. So if that one is not equal to t at index I, sorry, this should be in the sorted one. So if we're looking at this one, then we check if it's equal to this one, and if it's not equal, what we can do here is return false. Close that off, close off the for loop. So again, we're going through every character in the sorted strings. We're checking if the character at the positions in S and T match. If they don't, we'll return false. And then at the end of all of that, we can eventually return true once we've checked through all the characters. So that's, yeah, our slightly better solution based on sorting. So now we're going to be looking at complexity of this. So we'll look at time complexity first. So depending on the program language, the string length thing can vary, but in most languages, I'm not 100% sure the reason why yet. It's something I have to look into it. But this is constant order. So these two operations are just constant time. The sorting here, if we were to use quicksort, I think this is going to be, I'm just going to double check this, but I'm fairly sure it's n log n. Yeah, n log n. So this one would be, because it's string s, would be s log s, where s is the number of characters in the string. And this one would be order t log t. Here, because we're iterating through all the characters in s, the runtime of this would be order s. This is a string this is a comparison of one character, not the entire string, so the runtime is always going to be constant. So if you look at our total time complexity, we have order s log s followed by, so it's going to be plus, order t log t followed by order s again. And remember, because strings s and t have the same length from this point onwards, we know that s is equal to t, because s represents the length of string s and t represents the length of string t. So this would give us a total runtime of, I guess, OS log S plus OS log S plus OS. And we can stop worrying about this because this is the thing that takes the longest time here, and these are one followed by the other. So the total runtime would be OS log S, I guess. So let's think about space complexity for this one. So let's go to green. So for space complexity, I'm not 100% sure on Quicksort, but I think it would take up a maximum space of order S or order T, but usually it's a lot less than that. And that's the only extra space that we're taking up really. And this is only in the worst case. We don't store this forever, we just delete this off after. So space would be order S. So yeah, this is our optimized solution right here. So we can capture this. And it's got a time complexity of S log S and a space complexity of order S. So we're going to do the first optimization we're doing is a sorting optimization. And that's this right here. You can also lock in our brute force solution, even though we're not going to implement it. So let's look at optimizing this further. So another way that we can do this is we can think more carefully about the first rule right here about having the same frequency of characters. And what we can do is we can make another optimization where we end up using a bit more space. And what we can do essentially is store the number of each character that occurs. So I'll sort of show you with the same example. So if we had string S being listen, string T being silent, what we would do is we would go through string S first, and we would make some kind of data structure. So I'm going to just have a mapping of character to count. That's a terrible line. And then we'll write down each of the characters and how often they appear. So we have L, and we've got it once. We move to the next character, I. So we write I down. We have 1. We move to the next character, T. That's 1. We move to the next character, E, 1, and then N, 1. If we were to do this for something else, like another anagram, let's say state and taste. So this would be something like, so we'd have S, a count of 1, then we move to T, so T would be a count of 1, A would be a count of 1, then another T, so this would become 2, and then another E, which will become 1. And all we then do is go through each of the characters in T, and we basically check that there are enough characters. So we look at S here, we see that there's an S here. Oh, I missed the S. So we see that there's an S here. What we can then do is remove this and move this to 0, so we can decrease this count. We move to I, see that there's an I here, remove this to 0. There's an L, remove to 0. E, decrease to 0. N, we decrease that to 0. And T, we decrease that to 0. So if we can go through the entirety of string T and not basically go into minus character count, it means they're a permutation. Let's go through this one as well. So if we look at T, we have a total count of 2 here. So we're going to take off 1 T from this. So we're going to reduce this to 1. We're going to go to A. There's 1 here, so this is going to become 0. We have S, 1 here, so this becomes 0. T, so we've got one t left, so this can become 0, and then e, we can see there's one e there, this will become 0. So this is also valid permutation. So that's essentially what we're going to be doing. And the data structure that we're going to be using for this is a HashMap, because it's very efficient, and the insertion and lookup time is always constant, order 1. So it's going to be great for this. So we're going to call this a HashMap optimization. So this is how, I guess, we're going to do it. So again, it's the method is going to return a Boolean, and it's going to be called check permutation. It's going to take in string s, string t. So the first thing that we're going to do is, once again, we're going to do the length check. So if s length is not equal to t.length, return false. So I'm just going to say if. I'm just going to write down length check here, because I want to save some space. But essentially, we're doing the same length check that we're doing here, this part right here. So once we do that, and we confirm that they're the same length, we can create a hash map. So this is going to be a hash map, and the mapping is going to be from character to count. So it's going to be a char to int mapping. And I'm just going to call this cm for character map. Then what we're going to do is we're going to look through string s. So I'm just going to say for char c of s. So this is basically like the for loop that we did here, but it just iterates through it and then sets s at index I to char c. And what we want to do is we want to say int count equals cm dot find c. So we try to find the existing count for that. If it doesn't exist, this question mark means we just set it to 0. So it's going to find it. If it doesn't exist, set it to 0. And then what we're going to do is cm dot insert or set, I guess. And we're going to set for character c, we're going to set it to count plus 1. So what's going on here is whatever we had, so we look at what the count is in this table. We check what the value is. If we don't have value, we just assume 0, and then we increase the value in there. So we've essentially built up this table by the end of that for loop. Then what we're going to do is look through the characters of t. So I'm going to say for char c of t. And what we're going to be doing here is we're going to say, again, int count equals cm dot find. And then we're going to try and find character c again. Otherwise, we're going to set this equal to 0. So either the value that exists or 0. And then what we're going to say is if count equals 0, return false. So what this basically means is if there's a character in t where we don't have any characters left from the table, it means that we've run out of characters and we should return out of it. And then what we're going to do is, otherwise we're going to say cm dot set, and we're going to set c to count minus 1. Close that for loop. And then once both these for loops have finished, we're just going to return true, which means they are permutations. So again, I'm going to just go through this quickly because it's a bit confusing. So we do the length check first to check that they're the same length. If they are, we create a hash map that maps from characters to integers. We go through every character in S, and if there's an existing entry in the hash map, we add 1 to that entry and set it. Otherwise, we just set it to 0. That's basically this. So we set count here, set it, we try and find it. If not, we use 0, and then we increase that by 1. And then we'll look through every character in T. We'll try and find it in the table. If we do, we decrease the count by 1. And if the count reaches 0 and we're searching for a character, then we can return false because we've run out of characters. So yeah, so if we think about the complexity of this, doing the length check, again, like we said before, it's constant. So this is order 1. Creating the hash map is also constant because we're not putting any values in there. Here we're iterating through all the characters in string S, so this is going to be order S. Trying to find something from a hash map is constant time, so this is order 1, and setting a value in a hash map is constant time because we just calculate the hash and set the value. Here we're iterating through T, so this is order T, but since S and T would be the same length, I'm just going to say order S here, where S is this length of string S or string T. Again, we find the value from a hash map, which is constant time. Doing a number comparison is constant time, and then we set the value, which in a hash map is also constant time. So our time complexity in this case is going to be order S followed by order T technically, but also order S, which is order 2S, which we can just ignore the constant and it just becomes order S. Now, in terms of space complexity, so this hash map, as you can see, we can insert values into it up to S times. So this hash map would be order S time complexity, because the maximum length of this hash map is the number of unique characters in string S. And if each character happens to be a unique character, like it is here, it'll just be whatever the length of S is. So we can't use any more space than that. And that's essentially all the space that we're using. So our space complexity is order S as well. So as you can see, this is a more optimal solution because we went from time of S log S to a space of just order S. The space complexity might not need to be order S here. This is just a maximum. It typically isn't. So we've actually got worse in space complexity. But again, this is also maximum, so not necessarily. So yeah, I guess this is our optimal solution. And how we know that it's our optimal solution is if we think about the best conceivable runtime, what that means is what's the best scenario that we're hoping to achieve. And when we're checking if strings are permutations, it's expected that we have to go through every character in one of the strings at least once. So the best that we can hope to achieve is order S or order T, where S and T are the lengths of the string. So we essentially achieved the best, in terms of the runtime, we've achieved the best possible result. And in terms of the space, we haven't really, because not really needing any extra space would be the optimal. But we've got the optimal time. So this is the solution that we're going to implement. So let's implement this now. So I'm going to be doing this in TypeScript. So I'm going to implement it right now. So this is going to be the method that we're implementing. So const check permutation. And it takes in a string S, which is a string, and T, which is also a string, returns a Boolean. So the first thing we want to do is the length check. So if I can get this to snap. So the length check, we just do a check seeing if s.length is not equal to t.length, then return. So if s.length is not equal to t.length, then we want to return false. The next thing we want to do is we want to create our hash map. We're just going to be using the JavaScript map, which is essentially a hash map. So what we're going to say is const cm is going to be a map that goes from, there's no character data type in JavaScript, so it's just going to be string to number. So character to count. It's new map. And we're just going to initialize it to start with. So now we're going to look through all the characters of string s. So we're going to say for const c, or let's do this const c of s. So we're going to go through every character, and c would be a string because, like I said, JavaScript doesn't have character data type. So what we're going to say is a count which is an integer, is going to be equal to a cm dot get. So we're going to try and fetch the value for that character if it exists. Otherwise, we're going to set this to 0. What's the problem here? It's not int, it's number in JavaScript. Okay, so then what we're going to do is we're going to set the value. So cm dot set, and we're going to set use the character c as the string, as the key, and the value is going to be count plus 1. So either 0 or whatever the current value is, and we're going to increase that by 1 because we've got one of those characters to work with. Then we're going to go through all the characters of t, so const c of t, and we're going to try and find the existing count. So const count is the number cm.get. So we're going to try and find that character again. Otherwise, we're going to set this to 0. And then we're going to be setting it, we're going to reduce it by 1 because we've used that character. So we're going to do count minus 1 like this. And one thing I forgot to do here is we can do if. So this is our second failure, pointer failures. The first is non-matching length, and the second is non-matching character frequency. So if count is equal to 0, we'll return false. And at the end of all of this, we want to return. So let's do some testing. So the way we're going to test is just a simple console log. And let's try one of the examples that we had here. So listen and silent. So let's try that. So and we can see that we have true returned to say that these two are, in fact, permutations. Let's try taste and state now. So taste, state. And if we run that again, that should also be true. If I were to change this letter to Q, for example, then run that, we can see that it returns false. We can also test it with some more complicated examples. So we can try a gentleman and elegant man. This has a space, so I'm actually curious how it gets handled. So a gentleman, elegant man. We run that. We can see true happens. Yeah, it's working correctly. Let's try this one as well, the detectives and detect thieves. Yeah, that works. If I were to add an extra space in here, we can see that it returns false. So our solution is working, and this is indeed our optimal solution, which has a runtime of I guess order S and space complexity also of order S. So I'm just going to call this HashMap optimization. I'm just going to lock that in as well. So yeah, that is our final solution for the check permutation problem. Thank you.